All right, might as well go and get started here. Um, if you're new to this channel, this video series, I would definitely recommend starting out at episode 1. It lays down what we're doing, what we're working with, some recommended things to kind of get accustomed to, used to. Uh, if you're enjoying, please like and subscribe. Hit that bell notification to get notified of when we upload our videos. I'm hoping to be able to do more videos in the future, cover other subjects, maybe other design software like such as Circuit Studio, maybe some 3D printing stuff. Who knows the direction I'll take this in. Uh, I do know I'm enjoying this. I enjoy sharing my knowledge, my information. I do want to push more stuff out there with this, especially with this particular series involving more of the ISO hook-ins, the quality management side of things. Maybe we could cover some of that in a few streams, videos that'll be in between while we're waiting on materials to arrive. Maybe I can do a couple of streams, videos where we can catch up on some of the ISO hooks, some of the documentation that we're going to need for this, that we want to do for this. Because when we order parts, we're looking at least week and a half, 2 weeks turnaround time for the boards, the stencil, and all the components to actually build up our first pilot batch. So we'll have plenty of time to do some catch up with other videos with the quality management, even maybe some kind of catch up on some project management stuff. Um, I just know a lot of viewers are kind of eager for this part of it, the design, the layout, and everything. And I don't want to disappoint. And to be honest, I kind of want to get this going too, because I'd like this project for myself. Um, it's something I would like to start using for my own projects, my own experimentation. I even have an idea lined up to use it when I get the uh, pilot board built. Something we can use to test the concept, throw some firmware on, do some testing with an actual in-world scenario. We'll get to that when we get to that phase. Don't want to spoil the fun, the surprise. So the last episode, the last stream, we realized that the 4 circuit connector, pluggable, from Molex isn't readily available. Decided to go to Same Sky, which is formerly CUI Devices. I've used a lot of their products in the past, and I'm pretty happy with them. They're lower cost, but the quality's still pretty good. I really like them. Um, so said I would go through, so I went ahead and fixed the power supply. I changed it from the Molex to the CUI to the Same Sky, and I did the same thing for the 3 pin on the RS45 circuit. So now all the external pluggables at this point are using the Same Sky pluggables. It just will stay consistent throughout the design, throughout the actual final build. They'll all be blue plastic, so everything will match, and it's better aesthetics in that aspect. To just go and make the switch. Plus, they're lower cost, so the overall BOM cost to be much lower, which will be helpful because we do have a budget. Again, we really haven't spent anything but time doing this. I'm not logging my hours because this is for me, for myself, my little side project, my little side company that I do. So we've got all this tied up. So now we need to kind of start focusing on a few other things, but I do want to tidy up a few things on the ESP32 because I realized I made a mistake. I made an error. Ooh, imagine that. We need a boot mode pull up, and that is on IO0. So I'm gonna pull that out. So what we're gonna do is kind of shuffle some of the stuff around. Again, we haven't laid any traces. This is the design phase. No big deal. No harm, no foul. I notice I put this enable pin here, input here. Don't really need it with these 3 control inputs. 3 control inputs are more than enough for what we're trying to do. So I'm going to get rid of that. What we're going to do is I'm going to move these guys down. And since IO34 is an input only, this solves that problem. This is the perfect spot to fix any mistakes. All right, so that means I'm going to go and move the RS45 stuff down. To do pins. So that leaves these guys free. IO0 is going to be boot mode. So it's going to be pulled up to 3.3 volt with a 10K, but it also will be controlled via the UART to USB bridge chip. It's going to be the similar chip, if not the same chip, used on the ESP32 dev kits to basically allow you to connect to a computer and basically get a USB COM port, and then you can do your programming where it controls the enable and the boot mode pin to basically put it in bootloader mode so you can firmware flash it. So we're going to go and do that. So let's go and pull this guy out. All right, and we're going to throw a net label on there. And where are you, net labels? Net labels. So we're going to boot mode. That way we know what we're doing. Throw it on this guy. Bam. So that net is boot mode. I think, let me check my reference diagram here, my reference drawing. Yeah, we're going to pull up with a 10K resistor. I think I've already thrown those into the components here. It's going to be RC0603. All right, so here's something I screwed up the part number of. So it should be R603 10K. That's my fault, my mistake. Let's see here. For consistency's sake, for doing things the right way, let's go back here and fix it. RCO603. Let's see right here. We're going to rename it. 3. Save that. Let's go into properties. So what's funny is I named it properly in the properties, so I don't really have to worry about too much. Now, hopefully that doesn't monkey up anything on the schematic. We'll go through and look real quick before we get too far ahead. Let me throw that in here. Our CO603 10K. It's real easy to monkey this stuff up. Go through this guy here. We're going to copy this. And then we're going to just throw this guy over here. Oh, nope. See if I can drag. There we go. Got rid of that section. We're going to throw the other. Boot mode. I'm going to have to connect these two guys together. Boom. I mean, I'm being the ultimate lazy. Let's just do this the right way. What I will want to do then is but we're going to need to pull a port off of that. We're going to need to throw a port because we're going to be handling that off page. So then there. Not the cleanest. It's technically an input. Okay. All right. So we got the boot mode. We've got the pull up. We still have 2 free GPIO pins to use for other things. We'll leave them undefined right now in case we see something else we want to add, change, modify, whatever in the future. So now, let's go back to our cover sheet, our hierarchy. Upload a new one. Actually, before we do that, sheet properties. Okay. Properties. Properties over here, make it a little faster. You know what? Let's just make our lives a little bit easier. Projects, stepper controller, wrong button, hardware, stepper controller. Let's just grab this. We're going to rename it. And I'll show you what we're going to do. Back to the root. So, all right. This is going to be USB UART. USB UART. All right. Get rid of that for now. All right. Save it. Okay. So that is going to be our USB UART interface. And let's see here. So like I said, it's going to be the same chip used on the, see if I can remember it. It's going to be CP 2100 QFN, I think the 20 or the 20R. I think this is it. 20R. Don't really know the difference between these two. They're both quad flat, no lead, 28 pin. Yeah. So let's double check the data sheet. Typical connection diagram. All right. Let's double check our pin diagram. Yep. RTS and clear to send. Those are the 2 handshaking signals that we need. That's the primary reason we're choosing this chip. It's pretty much the same one used on the ESP32 dev kits, the official dev kits, because we need the RTS and CTS. That's how it controls the programming line, the auto bootload mode. So it'll, or is it DTR? I can't remember. I know it needs the handshaking and the other control signals to handle the bootloader mode. So let's go ahead and pop the. This is gonna be a fun one. Fortunately, we can download the models. Worry about throwing everything in there when we're done. This guy's a load of fun. Extract all. I'll probably have to look up a reference diagram on the um, which exact handshaking signals I need to tie in. Okay. Okay, so I've got that extracted. Please have the KiCad. You're a lifesaver. So let's go back to here. Close this guy out. Close this guy out. All right. So it's going to be that. Let's see here. It's a QFN 28 package, which is actually very common. So let's go to footprints. Let's get that guy in here. File, import, footprint. Pull you in. Yeah, we'll keep the IC designator. No reason not to. Save. Control V. Components. QFN 28's a standard package format. All right, we're going to go to File, Properties. We're going to get the step file. Get that guy loaded. Beautiful. Pin 1 indicator lined up there. I think that is a beautiful thing. I'm going to save it and go down to the schematic. We're going to File, Import Symbol, only because this is going to be a pain in the butt. KiCad. All right, so we've got the symbol. So we're going to rename it. We're just going to put U before, which is typically the we'll fix the organization of the pins here. I don't like this. A lot of times they're set up in the order around the chip that your pins are. It can be helpful when you're trying to plan like layout and stuff, but to be honest, not really. Not with a chip like this. It's not like it's a ESP32 or another chip where you have user-defined pins. They are what they are. So beneficial doesn't really matter. So let's go ahead and, again, I know I end up changing these. Get rid of that. I don't like just flooding everything. Let's get this footprint changed. QFN 28. Boom. We'll leave that as IC. Value is the same. That. Okay. One. Starting to remember these by heart. And for the sake of it, we'll just leave that in there. Okay. So that's Silicon Labs. Labs. This is their part number. Mouse. Their part number 355 and 131. All right, so that's all that's there. All right, so USB interface IC. It's a USB to UART bridge. I love it how it already gives a temperature rating. I just me being. And in case you want to know how I'm doing the degree symbol on a Windows keyboard, at least, you hold down the Alt key and the code is 0176, and that generates the symbol typically used to indicate degrees. So USB to UART bridge, QFN 28. Not much we really need on that. All right, and you know the drill. To Odo, new product. Sale. Let's see here. 355. Oh, you stop doing that, Odo. It's not an MCU. So we're just gonna IC. Reference. Basically the description. Purchase. A lot of lather, rinse, repeat. But again, you do the work now, and you ain't got to worry about it later. Bam. All right, so that's in there. All right, okay. Now, let's clean this mess up here. Get these guys out of the way. Blah, blah, blah. Nope, nope, nope. I'm just throwing stuff away, or just dragging out of the way. Boom. All right, get out of the way. Don't like looking at you guys. Stop. There. All right. So, okay. This is where the data sheet will come in handy on some of this. But in a nutshell, let's get these guys kind of out of the way. I don't really care about. Oh. Order or anything, because again, as long as your pin designator that matches the pad designation and the footprint, it does not care what order you have this stuff in. All right, so let's get the data sheet for this guy. Oh, this will help kind of determine what would be a little bit easier. Okay, so typical power connections. All right, so let's see what we got here. 1K pull up on a reset B pin, so we'll have to make sure we do that. Okay, here we'll make sure. So there's a couple of ways we can tie this in. Where we are, let's see here. So VBus, bus powered. We're not really bus powering this. Okay. We realistically don't need it powered by the VBus. But we can. And that would isolate the power supplies, which would be fine. So what we're going to do is we're going to follow this connection to connect it. And then because of the way everything's going to tie together, so there should be VIO, I think. There is no, let's see, VDD, let's make sure. VBus. Okay, so here's VBus. Okay, VDD is probably VIO. Let's double check that. Let's make sure we're on the right page here. Okay, VIO. We want to make sure we've got everything correct. So one of the things that this I've learned with using this particular IC is you want to make sure, you know what? I'm going to file. Let's see here. I'm going to see if I can find. I want to make sure I'm going to wire this guy up properly. Oh, do I have? All right. No. Trying to find. Trying to find what I'm doing here. Trying to find. So I want to make sure I'm wiring it up properly because it's so easy. Don't mind me. All right, let's see here. I want to make sure I have. Okay. Okay. All right. Okay. So I'm looking at a reference for an existing for a project I worked on before to make sure I have this right. Okay. Yeah, so we'll need. Well, there's going to be a bunch of no connect. Should be fine there. So VDD. Let's get you up here. All right, let's get these no connects kind of. Hey, stop. Kind of moved out of the way because we have our grounds. Ground 1, ground 2. See, so let's see if I can find that here again. Okay, so typically this type of package has what's called an exposed pad, which is this big center guy right here. That's typically tied to ground. Most of the time, it will be tied to ground, and then a lot of times they'll have one of these pins also tied to ground. That's why the schematic symbol has more than one actual ground pin. We're going to rearrange these. Okay, so V bus. V bus, V regin. They go together. Okay, all the no connects will kind of cram them together. Hello? Come on. Come on. All right. To suspend. 9. Okay, this is the reset pin. DCT. Okay. Sorry, it's just taking a minute to kind of organize this in a way that makes sense, because part of the thing is we want to be able to actually schematically connect to it without too many over complications. We just want to make it a little bit easier to read and follow through. So let's grab all the no connects. Oh. So we need DTR. DTR. We need that one and RTS. Okay. So those are the two control pins we need. Those will handle the auto programming, and we'll get to that once we actually start throwing this into the schematic. So we have the no connects. Let's see here. No connect. I think we can make our lives a little easier on this. Unless we'll type. Why don't you just do that? Unconnected. Huh. Boy, that would make life a little bit easier. And we just set this to unconnected. Because then we don't have to worry about putting that directive in the schematic. What I have a feeling is with all these unconnected. So let me look at something here. Let's see. Pin 21. All right. I see. So the 28 and the 28R, they have different options that you can set up. The 28R has some of these pins can be programmed as GPIOs to do special things like toggle LEDs to show communication, or especially control RS-485, like be a bridge chip for RS-485 communication, and with a RS-485 transceiver. So a lot of these unconnected pins in this diagram are used for other things in the R version, but we don't really care because we don't need all those special functions. We just need the handshake and the flow control pins, your USB data pins. Yeah, we don't need anything too special. Hello, I didn't see that NC11 down there hiding from me. Uh, and unconnected. Okay, so I'm just kind of referencing how I have it set up. And the 28R doesn't really matter a whole lot. Okay, VBus, VRegin. Okay. Yeah, so VBus is essential to be tied to um, the USB port, the actual USB port itself, the connector. That tells the IC, that tells this chip that it actually has a valid USB connection, that it is actually tied to a USB port. Without it, the chip does not operate, and I found that out the hard way. So what I'm going to do is I'm actually going to move that down below. Be a little bit easier during the actual schematics. So these are USB. All right, VDD, VRegin. Oh. Let's look at that diagram. Kind of look here. Now VBus, VRegin, blah 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 blah. D plus D minus. Okay. Decisions. All the handshake signals. All right. Clock. Move you up here. All right. With the reset. Oh, what a mess you guys are. Loads of fun. Hello. There we go. Reset. Move these guys up here. DCD. Okay. So bring in our USB differentials. All right, these are we will not be using those. Here's all our handshake signals. Hello. Stop. Stop being so finicky. handshake signals. All right. VDD, VRegin, VBus. Our differentials, all our handshake signals, flow control, modem control, chip specific controls, which won't get reset, which just gets pulled up anyway. All the no connects that are no connect, grounds, okay. As if moving this is going to make it even neater, it's fine. All right, so we have that guy. In the middle of so many things, I forgot to be at. Okay, all that's done. Perfect, beautiful. Save it. Go to here. We're on the UART bridge. Let's throw that guy in. Oh, why is it telling me footprint not found? The footprint's there. It's upset at me for something. All right. So let's throw in a few of our power ports. Man, I can speak. Grounds, at least one. Okay. So we know for a fact that we have this fella tied here. These two pins tied to ground. Know that for a fact. We know we're going to need to pull this reset, which is active low. We're going to need to pull it up, and I think they recommend a 1K. So we're going to find a 1K. Is this? I don't think we have one in our inventory. Let's double check. I'm going to tell you we don't. We don't have a 1K. So let's go find one. Resistance. Again, this is another value that you could 1K, 10K, 1K, apply filters. This we use like water too. We're not really pushing a lot of current. It's basically just for voltage. That reset pin does not really pull anything through it. Let's see here. 0603. That's fine. Tolerance isn't extremely important. So let's just look. Vichy. 10 cents. Pretty good stock there. Yagio, 10 cents. Pretty good stock there. So we'll go with the Yagio. Just because a higher stock. It's just, you have a better chance of finding it in stock. So it's a 1K. So here we go. Components. Nice, that's an 0603, right? Yep. 1K. All right. 603. Copy the duplicate rename symbol. All right. 0603 1K. All right. K0. What's your voltage? 75 volts. 100 milliwatts or 75 AA. Okay. Save it. Files. Properties. Footprint's the same. What's your tolerance? 5%. Bop. Bop, bop. It's a 55, 155, Q. Q200. Don't have to change anything there. It's a Yagio. Let's go and change this before I forget because I've done that before. Let's go and grab the manufacturer part number. Let's grab the Mauser part number. And it's 10 cents and 031. Wow, look at that. Alright. Alright, well, let's copy this. Because you know what we got to do? Oh no. No. Alright, bop. Nope, bop, bop, bop. Stars. Reference. Stop it. Oh no. Stop it. Purchase. Alright. Bam, 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 bam. Alright, go back to here. 1K, alright. Okay. Save. Well, back to our schematic. Our CO603, 1K0. Unless I screwed that up. Oh, I was looking at the already placed. That's my bad. 1K. Bam. Pull that up to here. Oh. Get that plugged in. So that'll keep it from hanging out and reset on us accidentally, something we do not need. Now those are all new connect. So we're going to want some filter capacitors over here on the VDD. We've already got a bunch of them in here. 0603, 104. All right, and then CCO 603. Let's throw one of those guys in there. All right. And I need a couple more off the V bus. So 104. All right. So that's off the V bus. All right. So, hey, stop it. Let's get this kind of cleaned up here. So this is going to go to VBus, VReg in. Kind of drag these guys up here out of the way. Kind of move you down here out of the way. Move you. Nope. I'll just kind of move you over here out of the way. Kind of sit there and look pretty. All right, let's get you plumbed in. Filter caps. All right. So that's our VDD and VReg in. So basically, we're just going to be powering it from the 3v3 line. Now we need to handle our V bus. Okay. So the data sheet showed a voltage divider. 22.1K and 47.5K off the V bus. Basically, that is the pin that lets the chip know it's actually connected to a USB port. That's just a voltage divider. We could do the math to figure out what it equals out to, but I think it's just, it says it here what the voltage is. Yeah, IO plus 2.5. This is just to make sure it stays within a safe range for the chip and it won't hurt it. So we're going to go find those two resistors. 22.1K. Alright, return the search results. So this is going to be easy. 22.1 space K. Bam. Bam. Alright, 0603. Man, it just comes down to price and availability. Panasonic, 37,000 in stock. Vishay, 50,000 in stock, 11 cents. I mean, I'm not going to split hairs over a penny. Just to make sure, stock quantities are healthy. Yeah, the traditional 3-digit code for resistors get blown out of proportion. They're doing all kinds of things now, like 22K1, 22.1K. We'll just follow that in our naming convention. It's fine. It doesn't hurt anything. We'll just amend all the documentation to reflect that appropriately. But you know what time it is. It's time to add that to our resistor. So here we go. We're just going to duplicate that. We're going to rename it R603 22K1. What's the voltage of this fella? 75 volts, and still the same. All right, we're going to get that. We're going to save it so we don't forget about it. File, properties. Go fix that here. Fix this here, 22.1K. Fix this. 75 volts. What's our tolerance? 1%. 55, 155. Let's not Q200. 55, 155. It's not Q200, so let's get that out of here. And it's not a Yagio. It is a Vishay. Mauser part number 11 cents and 009. All right. Bump, bump, bump. 22.1K. Beautiful. So, you know what we got to do now? Go to Odo, enter the part. It'll just save us the hassle along the way. That way this is done, and we don't have to wait till we get the BOM exported from KiCad to enter the parts into Odo. Which you could do. You can always wait and kick out the bomb out of KiCad and then add them to Odo off that. It just gets to be a pain in the butt. You might as well do the work now. Just get it out of the way. Just pull the Band-Aid off now. That way it's done out of the way. Boom, boom. 22.1K. Save. Let's just go over to our schematic. Edit RC 22K1. Fix all that later. Now we need a 47.5K. It's always these oddball values that really drive you nuts because most of the time you're gonna have to add them to KiCad, to your library, and to Odo. It just 47.5K. Bam. Again, comes down to price and availability. 13 cents isn't bad for KOA. 3,000, 9,000. 10 cents Panasonic. 68,000 in stock. Sounds like a winner. Let's just go that route. Seeing that's a 47.5K. So we can do 47K5. Which I think we'll do. We'll just go ahead and name it that. So let's go back to here. Components. We're going to duplicate that. We're going to rename it. Lather, rinse, repeat. So it's 47K5. 0603. Make sure our voltage is the same because they can be different. It's 75 volts. 1/10 of a watt. 47.5K. Oh, up here. Let's just go out. Because I always forget that. Bam. 75 volts. What's your tolerance? 0.1%. 55 and it's Q200. That dash 200 or just 200? Q200. I think it's AC dash. Okay. So we're at Panasonic now. Wee. Mausa. 10 cents and 042. And their part number for 7.5K. Okay. Copy that, paste it, save it. Bam, go in here. RC 47K5. Bam. All right. Now we're going to need to add another PowerPoint for the V bus, or PowerPoint. Well, I mean, technically that's what it is. All right. I think we could rename it. VDC. You know, I don't like the way that symbol looks. Wrong button right here. Let's just grab this guy and see if we can rename it. Are you kidding me? Oh, value. We're just going to call it V-Bus. Boom. All right, cool. V-Bus. It's only going to be used in a couple spots. That's the V-Bus that comes in from the USB port itself. Oh, so we're going to kind of, hey, come on, play along here. So we have that 22.1K comes in. 47.5. Stop it. All right. That comes in. All right. Copy you. Okay. Beautiful. Oh, I like doing that. I don't know why. It's just something about it. Boom. Oh, weird. All right. Cool. So that's our V-Bus input. Again, that just tells this that we are connected to a USB port. We might have room on this sheet to throw in the actual USB connector. We'll try. If not, we'll just throw on another sheet. I hope we do. Maybe we can drag things around. We'll see. So, other signals that we need are D plus, D minus. Those are going to be ports, basically. USB D P. USB DN for negative. I don't know why I bothered with that because I should actually make them bidirectional because technically they are. All right. DP, D negative. Now, technically, if I'm not mistaken, that should be 120 ohms differential pair. Now, typically I try to lay these boards out with these type of differential pairs so the length of the bus wires are as short as possible. And to be honest, a lot of research has come out. A lot of people have been researching the whole idea of differential pairs and PCB alignment and stuff. Um, a lot of people get overly concerned about making sure their differential pairs are properly impedance matched for proper coupling, things like that. But from data that's starting to show, it almost doesn't matter. So you're not going to ever get good coupling on a flat plane such as a PCB. You're just not. The real coupling comes in the twisted pair and the properly manufactured cable assemblies used in things like this. That's where you get your true coupling, your true control of the differential pair signals. The best thing you can do is make sure your lines are clean, going from like point to point. Minimum to no vias if possible. Try to limit it to just one or two vias. Try to do your best if you're on a multi-plane board to do proper differential pair, like for your impedance control. But for lower speeds like this, you're almost wasting your time worrying too much about it. This is only going to be used for programming, uh, maybe some um, debugging, really depending. This particular USB port, it's not for serious data transfer. I mean, you could use it down the road, but we're not talking super speed. We're not talking something that needs like in the megahertz range uh, to speak to something like a memory chip or a high speed bus for like a MIPI camera or something. You're to overly worry about differential pair routing for something like this is just a waste of time. It's just going to give you a headache and heartburn. Um, you're just spending time unnecessarily overly worrying about it. As long as you have good clean signals, the data gets to its destination as cleanly as possible. It almost doesn't matter. Um, Now, if you're at higher speeds or a lot of parallel data transfer, like what you'll see with like a MIPI camera, then yeah, you want to pay attention because you also have to worry about your bus lengths, your actual trace lengths. They have to be within a certain distance of each other because they have to kind of match as best as possible among the parallel lines, so you don't run into latency issues. So the data moves across the bus at a uniform pace, a uniform rate, because you can run into latency issues at high speeds. But something like this, a low speed, I've never worried about it. I don't put too much stock in it at these low speeds. I've never had a problem. Never. I've never run into an issue where like, oh my god, it doesn't work. Oh my god, no, I've never had that problem. It's always worked. So, yeah, I'm not going to worry about that. There's also enough room on here to throw in the auto program circuit, kind of down here in this area too. So I'm going to pull out the lines that I need. So I know we need DTR and RTS. And we're just going to go ahead and throw net labels on it. RTS. And another net label. DTR. All right. Okay, so we also need ports for these guys. So, yeah, let's make sure what we name them. ESP, TX, and RX. TX. So, now if you recall anything about UART, you need it to be reverse. So TX will actually go to your RX line, and ESP RX. And RX will go to your TX line. So, stop it. Okay, and those are ports. RX. Technically, it's coming. Okay. All right. So we've got that. Again, we might actually have the connector on here, so I might not worry about it. Let's throw in the directives real quick. The no connect directives on those guys. Directive labels. It's not what I'm looking for. View. Don't need the interactive delete tool. Oh, right here. No connect flags. So TS, DSR, suspend that guy, and alright. So those guys are do not connect. We don't have to worry about connecting anything. That way, we can do an ERC and electrical rules check, see if it flags anything, like any open pins, anything we might have missed. All right, so I'm going to go and end the video here. We're already an hour in. We'll pick up in the next video. We'll plumb in. We'll get the parts for the auto programming. Grab those parts. We will find the USB, get the USB connector, get it plugged in, and plumbed up to the circuit. Getting all that done. Hopefully, move on from the USB UART and get this finished out, and maybe actually start plumbing up the plugging in the stepper motor controller. I mean the driver IC, and then figure out some of the other ancillary stuff that we need to do, such as the fans and things like that. So we're getting close to finalizing the schematic capture on this device. Still some stuff to do. We still have to capture, like I said, throw in the stepper driver chip, finish up the USB UART interface section, and some ancillary stuff, such as like the fan connector, figure out what we want to use. I'm imagining something like a JST connector for that. I use them already on other devices and other projects, so I like them. And I've got like a little wiring little kit to make up my own headers and stuff, so that's not a big deal. It's just a little bit easier to deal with. Yeah, we're getting close. We're getting close to actually start the PCB layout. But for now, let's call it quits. I appreciate everybody checking in, checking out the videos. You have yourself a great afternoon. See you next time.